Welcome, everyone, and thank you for joining this talk on the greatly successful and ubiquitous technology of PCI Express. My name is Arjun Bangre, and I'm the Director of Product for PCIe controller IPs here at Rambus. In the next 30 minutes or so, we are going to take a look at the benefits that PCI Express offers to you in expanding your I/O bandwidth and how, by utilizing our IP, you can accelerate your time to silicon. Peripheral Component Interconnect Express, aka PCIe, is an interface which is used for connecting high-speed components. Today, it is the de facto interconnect between CPUs and peripherals in computers and servers. Lately, with newer form factors such as the M.2, we see PCIe being applied and used in mobile handheld devices and also in IoT. The specifications are developed and maintained by an industry consortium, an open industry consortium called the PCIe SIG. Today, the PCIe SIG has well over 800 members who develop interoperable products based on the specification. This year, PCIe SIG celebrated their 30th anniversary. So you might ask, where is PCIe used? Now, PCIe has found wide use cases in several segments. To begin with, in HPC and cloud computing, there's a burgeoning need for boosting the compute power as well as expanding I/O bandwidth. PCI Express is the interconnect of choice that is able to scale and meet this need. PCIe has also emerged as the leading interconnect for connecting enterprise-class SSDs to scale up storage needs in modern data centers. In networking, you would see SmartNICs and DPUs, which are utilized for specialized applications such as deep packet inspection, encryption, compression, or TCP acceleration. And such devices or chipsets use primarily a PCIe interface to connect to the main host CPU. We have heard about AI ML applications every day in the past 5 years or so. And as you know, AI ML applications have this tremendous speed and feed needs of data of over 1 terabits per second. Most modern host CPUs have several PCIe lanes, and this enables you to scale up your AI ML acceleration by designing accelerator chipsets meant for speeding up and working on AI ML algorithms. Next, as you can see, because PCIe is so ubiquitous and there are so many devices out there which use PCI Express, there is a very strong need for testing and measuring such equipment and making sure they are all robust and spec compliant. So there is a big market with several providers in the test and measurement space for PCI Express. Lastly, in automotive, we see that PCIe has been adopted in intra-ECU subsystems, such as like the infotainment systems. As new applications in automotive are getting to scale, like the ADAS and self-driving, you can imagine that SoCs are getting a lot more complex. Now, PCIe can also be used here to connect different ECUs, have redundancy, provide a reliable and high bandwidth connection, as well as scale performance. We'll see a table here which delineates the evolution of the technology. It is the history of PCIe as we know it, beginning in 2003 here in the first row that you can see on the top, where the Gen 1 specification came out, which supported a line rate of 2.5 gigatransitions per second per lane. It used 8-bit, 10-bit encoding, and because when you use a lane, a link with 16 lanes, you can achieve bandwidths of up to 32 gigabits per second. The next step in this technology was in 2007 with Gen 2 with 5 gigatransitions per lane. And in 2010, we moved to Gen 3, which changed the encoding scheme to 128-bit, 130-bit encoding. The evolution continued till 2022, where we had another disruption and changed from 128-bit, 130-bit encoding to 1-bit, 1-bit. Now, this latest specification, which was introduced in Jan this year, supports 64 gigatransitions per second per lane. And by using a 16-lane wide link, you can get bandwidth of 1 terabits per second. Now, as you look into this table and the years in which these specifications were released, there's one thing which is consistent, and that is innovation. Now, let's take a double click, make a double click into the key features of the 6.0 specification. First up, like I said, it doubles the bandwidth from the previous Gen 5 speed of 32 gigatransitions per second to 64 gigatransitions per second. It makes use of PAM4 signaling. Now, this enables the electrical transceivers to continue using a Nyquist rate as the same as Gen 5, but achieve this higher bandwidth. It introduces a low latency forward error correction, or FEC. Now, as you use PAM4 signaling, the bit error rate would tend to increase, and to combat that and mitigate it, we would need a forward error correction. The spec also introduced fixed size FLIT encoding, a higher bandwidth efficiency because of using FLITs. Now, what FLITs are flow control units. These are fixed size units of data transfer. And because some things such as the DLLPs and CRCs are amortized over a fixed size packet, you can get to increase the bandwidth efficiency. Like all the other specifications, this is backwards compatible to all the previous gens, all the way back till PCIe Gen 1. And in terms of channel reach, the Gen 6 is able to reach close to the reach on system boards as that of PCIe 5. So PCIe 5 offers about 36 dB channel reach, and Gen 6 is not too far behind at 32. Now, let us again compare and contrast some of the key technical metrics and parameters between the previous generations and the current PCIe 6.0 specification. In the previous generation, the modulation that was used was NRZ, whereas in Gen 6, we use the PAM4 signaling. So as this diagram shows here, the PAM4 signaling uses 4 voltage levels to encode the data. And as a result, you have 3 eyes as opposed to the 1 eye that you could see with NRZ. Because there are 3 eyes and their eye sizes are going to be smaller, there could be higher bit error rates. And like I said, to combat this, Gen 6 introduced for the first time the forward error correction. So forward error correction entails transmitting redundant data along with your actual data so that the receiver can perform some self-correction, self-error detection and correction. The PCIe Gen 6 introduced the 256-byte flits, whereas the previous generations, the TLP sizes could be anywhere from 0D words to 1024D words. Gen 6 introduced a new low power state called the L0P, and we are going to delve into that a little bit more in the coming slides, whereas this was not there in the previous gens. And in terms of the interface between the controller and the PHY, there is a specification called the pipe. And for the Gen 6 speeds, the pipe specification was upgraded to pipe 6.0. And this is what supports the new SerDes architecture, where the encoding is done in the controller and not in the PHY. So why do we need forward error correction? If you go back to that discussion about the multiple eyes and the higher bit error rate, this pans out to be around 10 power minus 6, as opposed to a much lower bit error rate in Gen 5s. And to compensate for this, we do the forward error correction. By doing this, we avoid the packet replace that could occur for every bit that could get flipped, and thereby eliminate inefficiencies. So this lightweight FEC works in conjunction with a stronger CRC, 8 bytes, which is new, to keep the link retry probability at 5 into 10 power minus 6. Now, the FEC design considerations were thought about with a goal to keep latencies to 2 nanoseconds or below. And the fact that we have a fixed size flit has made this design be more deterministic in terms of latency, as well as contained in scope in terms of complexity. So what is new with this new power state called the L0P? Now, L0P offers us a seamless way to reduce the number of lanes which are transmitting data at any given time from, let's say, a by 16 to a by 8, by 4, or by 2, and then expand back up when you still require the bandwidth. So the case in point here is, let's say you have an application which does not need as much bandwidth as it had been, and it has throttled down the application data being exchanged. The link can enter L0P seamlessly and consume less power, which is in proportional to the bandwidth usage. This, like I said, does not impact the traffic flow. So while you have some lanes transmitting data, you could power off some lanes and power back on seamlessly without disrupting the ongoing traffic. Something to note here is this L0P is supported only in the flit mode, and the flit mode is the new fixed size packets, which is supported both at Gen 6 speeds and all the previous speeds prior to it. Now, let us understand why there was a need for security in the PCI space. Now, if you recall all the applications in the different segments, you could see the PCI link carries a lot of high value data. And because of this, it is a target, or could be a target, for physical attacks from malicious entities. And these malicious entities can use a threat model, which could be a rogue retimer. It could be a interposer or a malicious expander. Now, in order to secure and safeguard the data, we need to encrypt the data which gets transmitted on these links. And for this precise reason, PCI SIG introduced the IDE specification in 2020. Now, this is quite an eye chart here, but let's break it down. So what PCI SIG did was they did not try to reinvent the wheel. There was already a well-adopted protocol called the Security Protocol and Data Model, or the SPDM, which was developed by another task force or consortium called the DMTF. What PCI SIG did was it piggybacked on this and came up with a specification called the IDE, which is Integrity and Data Encryption. This specification can be broken down into three subcomponents: the blue diagrams, the blue boxes, which are CMA, the Key Programming Protocol, and the DOE. What these essentially are doing is they are defining the scope of the SPDM and in terms of a PCIe link. So, for example, the CMA is defining a set of rules and exchanges so that devices can identify themselves and authenticate using the protocol called the CMA. And then the Key Programming Protocol defines how keys that are used for encryption are exchanged using another protocol called the Data Object Exchange, or the DOE. What DOE is it's essentially a register mailbox mechanism so that the keys can be exchanged between the opposite devices on a PCIe link. The kind of encryption that IDE uses is the robust and powerful AES 256-bit GCM. So you can take a look at the PCI IDE spec, and this will lay out the rules of how the set of procedures that needs to occur to first exchange keys and then start encrypting the data. Now, given that we have understood what the new PCI Gen 6 has to offer, let's see how that translates into what you would need from a digital controller, which you could use to realize this interface. We now know that we'll need to support a 64 gigatransitions per second link rate, and we need a state machine which can allow the controller to negotiate this with another device. So being a Gen 6 device, you could be talking to a Gen 1, Gen 2, Gen 3, Gen 4, Gen 5, or Gen 6 device. And so you would have to negotiate that speed and then start entering a data phase where you could exchange meaningful data. You would also need to be able to operate both in the prior non-flit mode as well as the new flit mode. The controller would need to implement a lightweight FEC, which has a low footprint in terms of gate count as well as low latency. You need to support the PAM4 signaling and the new L0P low power mode. And in terms of the user interface, the logic that enables your own design to interface with the controller, you want the controller to use a standards-based protocol such as AMBA 4 or 5. You would want to see some configurability in terms of the data path width, as well as the pipe interface configuration in terms of degrees of freedom, so that you could configure your choice of peak clock frequency as well as the data width that suits your service. We also have a built-in need for RAS, which is the reliability, addressability, and serviceability, and the security feature, which is the IDE, which we just discussed. Here we have our Rambus Gen 6 controller IP, which we released in January of this year. This diagram gives a high-level view of the constituent blocks that make this IP up. So starting at the top, you see an AXI bridge layer, which you could connect to your logic. This is then in turn connected to the transaction layer and the data link layer, and followed up by the physical logical subblock. So there are two interfaces that you would be exposed to in terms of connecting to make your ASIC with a PCI interface. One is the standard interface on the user logic, and the other would be the pipe interface if you were to use your own SerDes. Rambus has a complete subsystem, which we offer both the SerDes and the controller, where we would integrate both the controller and the SerDes, in which case this pipe interface will also not be visible to you. So in the scope of the controller, we also have a optional IDE security engine, which could be integrated into your controller, and this comes pre-packaged with our IP. So to list out the features, we are compliant with the specification for PCI 6.0, backward compatible as required to PCI 1.1. We can scale link widths all the way from by 1 to by 16, and have a configurable data path to let you optimize metrics of power, area, and performance. Now, we let you do all of this by providing a powerful GUI configurator, which under the hood parameterizes the RTL and makes it very user-friendly to configure. We are compliant to the PIPE 6.1 spec. We support 128 PFs and 2K virtual functions, the FLIT and non-FLIT modes, IDE, as well as the optional interface here of AXI. Something to note is that we have controllers with both the AXI user interface as well as a native interface, where this block could be removed and you could directly connect here at the transaction layer, where you could implement your own customized AXI layer. We also have a mode which is called the transaction layer bypass, which lets you connect directly to the data link layer. Now, another very important feature that our customers find very useful is our same RTL code base has a configuration which can let you port it onto FPGA platforms, and thus make use of the IP to prove your proof of concept design or do some early pathfinding exercises. So we support RTL for both ASIC implementation as well as FPGA implementations. So given that you are in the need for expanding your I/O capability, why would you want to consider PCIe controllers from Rambus? Firstly, we have the expertise of more than 25 years of building PCI Express controllers all the way back to Gen 1 controllers. So the IP technology can be complex, and we have a very well experienced team which can simplify and give you proven IP which will help you accelerate your design cycle. We are flexible because this is a digital controller and it is process and fab agnostic. We have previously interoperated with several different PHY vendors, and so you get to utilize the benefits of those learnings. We have a track record of being utilized in designs with more than 500 tapeouts. We have advanced RAS features. Like I said, you could configure and tailor the IP to match with your specific needs. And lastly, in terms of prototyping, you could utilize our IP to port onto FPGAs and develop proof of concept or reference designs. So what are the key takeaways today? We have seen that PCI 6 improves upon PCI 5 in several ways. One, it doubles the bandwidth. Two, there's a higher throughput efficiency because of FLITs, and this is pronounced when you're using data payload sizes of less than 128 D words. It has a new low power mode, which can reflect power savings to your bandwidth utilization. And finally, you could utilize our IP that we have available since January of this year, and which has enabled several of our customers who are working on their Gen 6 designs as we speak. That concludes this talk on PCIe. I'm thankful to you for joining me here today. If you have any questions for me, you will see a pop-up box right about now, and you could post your questions for me there. You will also find a resources tab in this platform where you could download key technical collaterals that you might want to go through about PCI Gen 6 and our controllers.